Thank you. Oh, God. All right. I think I need to reduce the volume a little bit. Thank you very much. OK, well, thanks for coming to the talk. So I'm going to report about where we are with this problem that we've been working on for the past 10 years. And the problem has to do with experiments in which you take unconventional superconductors that have certain signatures of equilibrium superconductivity below TC, mostly in the Terahertz optical properties. You stimulate them in a certain way above the thermodynamic transition temperature, and you reproduce the features that you observe in equilibrium below TC within some error bars and some confidence. And so sometimes the size of the error bars and exactly the confidence are object of contention. But I will tell you my view of things and the way we're trying to develop new methods to try to explore this phenomenon in more detail. And we have at least one new measurement. So the talk is going to end up with new results that I'm quite excited about. It's not going to be super polished. It's the first time I give it. So just have a little bit of tolerance, please. Now, how does this work? Right. So this business has to do, is in the context of unconventional superconductors. And so imagine your favorite idea of the normal state, where you might have preformed Cooper pairs of some form, or you might not have preformed Cooper pairs. And the idea is to use a coherent drive to stimulate the material in certain ways. And you are trying to either enhance or reduce phase coherence between putatively pre-existing pairs, or to enhance the pairing field in equilibrium, for short or long times. This business of photo-enhanced superconductivity has a long history. In the 1960s, there's been these very interesting experiments in which certain microbridges of BCS superconductors were irradiated with microwave radiation at frequencies below the superconducting gap. And what they observed were enhancements in the transition temperature by some fraction of the transition temperature and enhancement in the critical current. There's a very beautiful theory by Eli Ashberg that posited that excitation below the BCS gap would redistribute the Bogoliub of quasi-particles above 2 delta, thereby fooling the self-consistent BCS equations to think that the material would be at lower temperatures than it actually would be at. And this would explain what the observations were. There's been also a lot of other work where irradiation of cuprates, for example, in the ultraviolet, has resulted in enhancement. Let's say if you would take an underdoped cuprate, you could observe transiently or in a metastable state the properties of a cuprate, of the same cuprate at a higher doping value. But in these cases, the people were not able to achieve effects that were not observed in that class of materials at the best doping. We've been looking at effects in cuprates and effects in a number of organic compounds. We've done work recently on these kappa BEDT salts, where we sort of reproduce some of the results. I'm not discussing this here. I will focus on the problem of potassium doped C60. This is the result of four PhD theses and one postdoc career. And so this is what I'm going to tell you about. So let me just focus on the problem of the Fullerites. This has been discussed in some detail during this workshop. Think about an FCC lattice of 3 times doped C60 molecules. This is, in the case of potassium doping, this is a 19 Kelvin superconductor. In reality, if you take cesium and you put it under pressure, you can reach transition temperature of even 40 Kelvin. Okay, so for a while, these were the highest temperature organic superconductors. The idea of the physics of the superconducting transition is one in which, when you take the 3 times doped fullerene, you put 3 electrons in the highest unoccupied molecular orbitals of the undoped C60, which really readily formed a low spin state because of Jahn-Teller distortion. So there's a dynamical Jahn-Teller distortions, an effect of correlations, and this promotes fluctuations in the different ways in which the singlet can occupy the various orbitals. And according to these studies, the interaction between the dynamical Jahn-Teller distortion and correlations gives rise to the superconductivity phenomenon. So The signatures that I will be discussing in the way we in at least the first half of the talk, in the way we diagnose the superconducting transition, have to do with the textbook optical properties of a S-wave superconductor. So if you now measure the reflection coefficient with amplitude and phase in equilibrium of C60, and you reconstruct the real and the imaginary part of the optical conductivity, what you expect from textbooks is the following phenomenon. You have a delta function, you have a superconducting gap. At temperatures below Tc, the reflection coefficient in equilibrium should become exactly 1 for all temperatures, for all frequencies below 2 delta. The real part of the optical conductivity, that's the in-phase response of the current to the electric field, exhibits a gap and has a pole at 0 frequency that tells you about the density of Cooper pairs. And if you measure at finite frequency, although you can't see the presence of this pole, you can tell that it's there because what you have is a divergent imaginary part of the conductivity, which has to do with the fact that real and imaginary part are connected by Kramers-Kronig. These are optical measurements that were done at Elettra by Matteo Mitrano when he was a PhD student with me. And you can see in equilibrium, when you cool down these powders that we have, you observe the formation of a gap at about 2 terahertz, an imaginary part of the conductivity that diverges because of this delta function at low frequencies, and a reflection coefficient of exactly 1. So because I'm going a little bit fast here, but the rationale at the beginning was, for lack of, without knowing what you're doing, because you know that these molecular vibrations are beneficial to superconductivity, what Matteo proposed was that you could use a mid-infrared pump and tune it around and try to drive certain modes of these molecular of these molecules, and whether the response would be linear or nonlinear in the driving field, it wasn't clear, but maybe one could either enhance or reduce superconductivity in an interesting way. That's the way we got into this problem. And so this is the way we do the experiment. It's a pump probe experiment. We pump in the first generation of experiments. Matteo pumped around here at about 7 microns. And then we would use a probe pulse that would interrogate the material here in the region of the gap, so where the difference between the metallic state and the superconducting state are particularly stark. This is the results. This is not Matteo's data, but I'm purporting it to be. Basically, this is the equilibrium optical properties when you cool the material below 20 Kelvin. And this is the transient optical properties extracted by measuring the reflection of the Terahertz pulse at 1 picosecond pump probe time delay. And what you observe is a very suggestive similarity with the equilibrium properties of the 0 temperature or low Tc material. I will point you here that within the context of this, within the limits of this reconstruction, what we observe is a light-induced divergent sigma 2, which has the same size as the one that you observe in equilibrium, suggesting that you are promoting a superfluid that has the same density as the one that you would observe at 0 temperature. Okay, so this is all that was good. Let me just now, I'm going to use in the next part of the talk one particular figure of merit. I'm not going to keep on showing you all these 3 optical properties. I'm going to take these spectra and I'm going to fit them with a Drude model. The advantage of the Drude model is that it can both fit without a gap. The Drude model can both fit a metal with a finite scattering rate and a superconductor with infinite scattering time, 0 scattering rate. So if you do this, you can basically take the limit of sigma 1 for omega that goes to 0 and take this number, sigma 0, which would be infinity in a superconductor, or rho 0, which is the inverse, which would be 0 in a superconductor, and use this to characterize the dynamics. So that's some of the things that I'm about to say. So this is now the response that we have in this putative extrapolated 0 temperature conductivity, which you determine with an error bar that depends on how low in frequency you can go with your transient measurements. But what you find is that there's a conductivity that goes from some finite value of the metal to basically 0. but only for a very short time. And this is, of course, it has all sorts of problems, including the fact that once you look at this fast dynamics here, you really have to be very careful in the way you fit the data. And at some level, who cares about making a photo-induced superconductor that only lives for 1 picosecond? So during COVID, we have actually done a lot of work in trying to do the same experiment using longer pulses. So this is one of 3 things that I'm here to report to you of new results or semi-new results. There's been a lot of effort in my group to use laser methods that allow us to drive, using CO2 laser technology, to drive these C60 materials with pulses that perhaps have the same area or the same integrated fluence as these short pulses, but are tunable in length, and hence would allow us to study how this effect would scale. I'm not going to tell you this. This is a big laser that Matthias Budin and Thomas Gebert built based on CO2 lasers and various, seeded by a femtosecond laser that allows us to do exactly the same experiment that we did before, but instead of pumping so this is the Terahertz probe, and instead of pumping it with a 100 femtosecond pulse, I can now make my pulse tunable between 1 picosecond and a nanosecond. So basically, now the experiment is done now at 10 hertz instead of a kilohertz. So the signal to noise has gotten a little bit worse. But what you can see is that whilst in the previous experiments, the effect would be confined to 1 picosecond immediately after the pump pulse, if you look, this is my pump pulse of 300 picoseconds. If you look at the transient sigma 1 and sigma 2 and reconstructive reflectivity at various time delays after this excitation with a long pump pulse, we observe a metastable state that lives for about 10 nanoseconds, which has, again, extremely suggestive features of a superconducting-like optical properties. So now this is my rho 0 that I told you about before. You remember I had a rho 0 that in the first experiments would go down in 1 picosecond and come back in 2. Now in these new experiments, you can fit the data, and you can extract this rho 0 that stays close to 0 for, let's say more than a nanosecond. Now we can negotiate on exactly what defines I should understand the relaxation time. But let's say this is sort of a metastable state with very low resistance. What gave us some degree of confidence that these fits might be appropriately reproducing the true zero frequency resistance, where what Matthias did was he sort of now measured the 2-probe resistivity, and with the caveat that we had to subtract away the contact resistance, and we assumed that the contact resistance would not be a function of time in the photoexcited state. And within a number of caveats, we've been as careful as we could, and we sort of found a resistance which is in the ballpark of 0, plus or minus some error bar, which is at least consistent with the extrapolated rho 0 from the optical measurements. So this was one of the 3 things that I want to tell you. The second thing that I want to tell you is that we've done a lot of work in Hamburg. So those of you that went to Ankit Diza's talk yesterday, they have seen, Ankit has hinted at the new developments in our group, where this is mainly due to Biao-Long Liu, who was a PhD student with me. He's now a staff scientist at PSI, who has developed a new optical parametric amplifier that allows us to generate narrowband pump pulses pretty much anywhere we want, and high-intensity narrowband pump pulses, which now enables us to systematically study, to excite wherever we want, from, say, a terahertz to the UV. So now this is recent work unpublished work by my student, Ed Rowe, who has really done an extremely careful job at reproducing Matteo Mitrano's data and Matthias Budin's data. Instead of pumping here where Matteo pumped, he has now done experiments by pumping at many places and doing the same reconstruction. What's really striking is that he discovered a much clearer resonance in the photoinduced state when he goes to excitation at 45 milliV, where he excites rather than tangential modes of the molecule, radial modes that modulate the radius of the of the molecule. So what he has shown here, this is an efficiency that I define in a way that I'm not going to tell you how, but let's say how efficient this process is. And what he has found is an enhancement of 100-fold. This is where Matteo was pumping. And he has now found an effect that is 100 times more efficient when you pump at 45 milliV, highlighting a dominant energy scale in the nonlinear response of this material. This is well shown. So this is the way we would plot, if you plot rho 0 of the photoinduced state as a function of fluence when you pump at 7 microns, what you found is that really you never reach anything in the vicinity of 0 if you wouldn't pump with at least 20 millijoule per square centimeter. With this new method, pumping at 45 milliV, we can reach the equivalent of, something that is suggestive of zero resistance at 200 microjoules per square centimeter. And this is also very reassuring because the average heating, and also heating immediately after the pulse, is also potentially 100 times smaller. There's less hot carriers. So we have a situation that is much better, under much better control. One of the striking things is that even at room temperature, when you pump at 45 milliV, you find optical properties that are suggestive of a zero resistance state at the highest fluencies that we can reach. Unfortunately, it's difficult to develop 10 terahertz pulses, and so the furthest we can get to is 300 microjoules per square centimeter. So this is where we are. So this is, again, you can see that the extracted optical properties at 295, say at room temperature, in the photoinduced state are, in the same ballpark as what you fitted for low temperature. So the gap is a little dirtier. Sigma 2 doesn't diverge quite as much, but it's still a very suggestive transient response. And these are, so this was part number 2. So in the last 2 years, what we found is that by pumping in the right way and harder, we can find a metastable state that lives for about 10 nanoseconds, and also with a resistance that is electrical resistance that is compatible with 0. The efficiency has gone up by 100-fold, and the effect appears to survive up to higher temperature scales than the 100 and 150 Kelvin that we discussed before. Right, how much time do I have? Fantastic. So the real talk that I wanted to give you is going to be in the following 10 minutes, okay? You can, as you have seen, those of you that were in the previous session, there's only so much that you can extract from fitting sigma 1 and sigma 2. And at the end of the day, is an unsatisfactory, you only can get partial things. And if you change the parameters of the fit, you could get different results. So, you fit it, you cross your fingers, and you hope that you've done everything right, and you just, report it within this. But what you really would like to see are the same features that you observed in equilibrium in true superconducting states on the ultra-fast time scales. The problem is that there's no technology that allows you to probe many of these things at the fastest time scales. So a lot of the efforts of our group is to try to push the boundaries of what is possible at the method level to try to explore, for example, critical current and Meissner effect. So the next part of the talk are most recent measurements on the possible critical current in this light-induced state, okay? The first time I give the talk, so the slides are a bit on the rough side. So what you need to do is you need to generate this state, which lives, let's say, a nanosecond. And now what you're going to need is a fast current. You need this current to be at low enough frequencies, so far below a terahertz, to expose, where you don't have excitations of the system, to expose the critical current response. And the problem is that the longer you go in wavelengths, in the lower you go in frequency, the harder it's going to be for you to do an experiment because the diffraction limit is going to get larger and larger. So 300 gigahertz is a millimeter, 30 gigahertz is a centimeter, lambda. So it gets very hard to do nonlinear optics experiments in the far field, which is all what we're used to do. So this is the work. There's been about 5 years of work. This is led by Erin Wang, who's a staff scientist in my department with Joe Adelina, who's a PhD student of mine, and Mariana Chavez, who's also been pushing all these experiments very aptly. Okay, so the workhorse to measure nonlinear current response is going to be not far-field electromagnetic radiation, but photoconductive switches. So basically, we resurrect 1975 Bell Labs technology, where, you know, what Dave Austin and other people showed was that if you take a semiconductor, you know, a sort of a semiconductor with no undoped semiconductor, and you apply a voltage across it, you know, you basically have no current if you in equilibrium. But if you photo irradiate it with a femtosecond laser pulse, you will generate a current. If the lifetime of the carriers is short enough, the conductivity will stay high for a short time, and what you will get is a picosecond or sub-picosecond current pulse, which you can then propagate along a strip line and try to do linear or nonlinear transport measurements. So basically, you know, again, the workhorse is one in which we will have at least pairs of switches. You have a switch here and a switch there, and you have a signal line here. You need to design the signal line so that this thing is not an antenna that radiates into vacuum, but keeps the electromagnetic field confined in the strip line. The first femtosecond pulse launches this current pulse, and then you have a second switch where you detect the effect by using a femtosecond pulse to bias the photoconductive switch, and thereby where you use the current pulse to bias the photoconductive switch, and you measure this with a femtosecond pulse. So, but this is, you know, this is typically this is not a brain surgery thing. Lots of people can do this. You can easily generate picosecond current pulses, and if this Austin switch is large enough, you can have these peak currents be very high. Okay, so that's what we're going to try to measure critical current with. So to do this, you cannot rely on the powders that we had before, but you have to learn how to grow C60. So that was part of this whole story. And basically, these are the fabrication steps that we have taken. You grow these Austin switches. So these are the photoconducting switches. These are standard growth methods. You deposit coplanar waveguides. You put a mask. You grow a thin film of undoped C60, you contact it, and then you read the literature of 20 years ago, and you evaporate potassium on it. You minimize the metallic resistance at room temperature, and this was shown by Zettel's group and by other people that if you do this at the minimum of conductivity of the metallic state, you get a superconductor. And so, you know, it's kind of hard, but if you do it long enough, you find, you know, a really nice, you have these thin films. This is, the transition is a little bit broad, but the transition temperatures is 19 Kelvin, where it's supposed to be. So it's, again, the qualities, some of the results, these are different samples than the one we used for the other experiments, but they are superconducting at the right place, and the densities are right. The Hall effect is what it's supposed to be, so they cannot be as different from the powders as, you know, completely different from the powders. So the first thing, now you can kind of start playing with this. The first thing you want to see is that if you take a metal and you photoexcite it, you're supposed to make the conductivity better. So you should go from a voltage drop of a metal to a voltage drop of a superconductor or a better metal. And so at these two Austin switches, so this is kind of my little schematic on how to tell you what to expect. You start, this is metallic above TC. You photoexcite it at 7 microns. This was the voltage drop on the C60. Imagine that I'm making it superconducting. I get a voltage drop here, only at the interface, and then there's 2 terahertz pulses that propagate, one to the right, one to the left. So if I measure this contact or I measure this contact, there's a DC current here that keeps the voltage drop onto these strip lines. So you're supposed the voltage should go higher to the right and lower to the left within a time scale that has to do with this transition. So you know, this is broadly consistent with what we expect. There is a transition from a metallic state to either a better metal or a superconductor. You know, this is difficult. I mean, there's now the problem of terahertz contact resistances and kinetic inductances, and this thing is going to ring like a bell. So doing quantitative measurements at these time scales is not something we've mastered. But qualitatively, we observe the right thing. So this is the linear volt. This is an ultra-fast voltmeter, where basically I'm doing the transition, and now I see the change. So now to the workhorse of the measurements. Here you put the C60. Now you want to have three Austin switches. One, which is a big one, which launches the current pulse. Then a second one that samples the incoming pulse as it's coming in. I want to calibrate the time and shape and intensity of the incoming current pulse. So these are typical measurements. And then this current pulse will go through, or it will get reflected, and will get reflected. And then at the second Austin switch, I can measure the transmission. So the first thing I can do is calibrate these terahertz current measurements as a function of temperature. So in equilibrium, so what I do is the following. I take the outgoing pulse, I take the Fourier transform, I take the modulus of the Fourier transform, and I divide it by the modulus of the Fourier transform of the incoming pulse. And so that will give me some sort of, yeah. Perfect. So this is what I should expect in a material that I know below 19 Kelvin becomes a superconductor because I've measured the 4-probe DC resistance. And what you will see, so now these, remember, compared to the optical measurements, what's great about these experiments is that they allow me to probe at frequency scales between 500 gigahertz and about less than 50 gigahertz. Okay? Above 500 gigahertz, you start having resonances of the circuit, so things get a little harder. But this is, a simulation of what you would expect. Here, there's some LC coupling here that gives you a resonance. But down here, say between 50 or less than 50 and about 300 gigahertz, you can characterize the response of the equilibrium superconductor. So in the superconducting state below TC, the transmission gets higher at low frequencies, whereas when you go in the metal, because there's dissipation at low frequencies, the transmission gets lower. So that's the only thing you need to take home. And the transmission becomes a factor of 3 higher at 0 temperature than it does at TC. Okay, I'm plotting the ratio of the whatever temperature measurement I'm making with the 20 Kelvin response immediately above TC. So now let's do the experiment. Instead of cooling, we go above TC, we pump this, and now, so we have now four pulses that are all synchronized. One induces the photoinduced state in C60. This one launches, this measures the incoming, and this measures the transmission. Again, this is linear response. And what you observe is a photoinduced effect. Remember, this number at 0 temperature was about 3. What you observe in these samples is a photoinduced effect, which is actually, we could not ever get it any better than the response of the equilibrium response of the material at about 0.8 TC. So this is about 16 Kelvin. It's a sloppy superconductor, and it's at some level it's just to connect back to the conversation before, it's actually indicative of a superconductor that is quite a bit weaker than the one we extracted from the photoinduced experiments in the powders. But yet it is positively, it does the photoinduced state does seem to reproduce the response measured at 16 Kelvin in equilibrium. Right, critical current measurements. This is the equilibrium critical current measurements. Those of you that do superconductivity are used to these curves. The critical current is, okay, these are integrated currents. They're of order a few 10 kiloamps per square centimeter. These are equilibrium critical current measurements with the terahertz pulses. Now what we can do is we change the fluence in this launching switch. You can see you probe it here and you do the experiment 3 times. The incoming current is either 1 number, 2 times that number, or 3 times that number. And here we measure the transmission in these situations. Again, equilibrium of the terahertz critical current. And what you observe that, for example, at 8 Kelvin, well below TC, the 50 gigahertz response drops from 2.5 to 1.8, say. in these conditions. When you go above TC, there's no effect, because the metal doesn't have just as a has a much more linear current response at these frequencies. Okay, so this is the pièce de résistance of the talk. This is now the photo-induced state of the putative 0.8 TC light-induced state. When you apply currents, you can see that so this is now, you excite this. This is the change in conductivity at 50 gigahertz. And these are the values of the response for currents of increasing amplitudes. You can see it at about 15 kiloamps per square centimeter, the light-induced effect goes down. And maybe these are preliminary data, but what is very suggestive is that if you take the critical current response at 16 Kelvin in equilibrium, and you show the critical current response of the photo-induced state, they're kind of on the same ballpark. You see a reduction that is comparable. So this is where we are. It's still a work in progress, but the other thing that I should tell you is that although I don't have the data here, if you do the experiment in the metallic state, and you excite it in the wrong place, where you take a metal and you make it another type of metal, this effect doesn't appear. And if you look at the results below TC, where the physics of this process are that you destroy the superconductor and you make a metal, this effect is also not there. So at least, this nonlinear current response of the photoexcited state is only limited to situations in which we've claimed that the photoinduced state was a photoinduced superconducting state. 130 seconds. So this is one experiment of 5 years of some people's lives. The other part of 5 years of other people's lives is an experiment which hasn't quite worked yet, in which we're trying to measure the Meissner effect of the photoinduced state. And this is how the experiment is done. So this is led by Michele Buzzi, who's a staff scientist, Gregor Iozzo, who was a postdoc with me. He's now become a faculty member at EPFL in Lausanne, and Giovanni De Vecchi, who's a great student of mine that came from the Milano group, from Giacomo Ghiringhelli's group. The way they're trying to do the experiment is, if this is the C60, what you can do is you can apply a field, and you can put a garnet here on top, in which you can use MOCI, magneto-optical Kerr effect, to measure the local magnetic field immediately outside the superconductor, and now photoexcite the superconductor and try to characterize changes in the magnetic field immediately outside the sample, and try to see, for example, if the material does become a superconductor and it is a diamagnet, you should get a reduction of the magnetic field here and an enhancement here. Because of expulsion. So this experiment kind of works on odd days and doesn't work on even days, and we don't entirely understand the observations, so I won't claim that this is done to any degree of confidence. Right, that's it. I just left this as the last slide. I really would like to sort of, high praise for these 3 people and other people in the department that have developed these new methods to try to, bring transport measurements to this non-equilibrium field. And yeah, thank you for your attention, and I'm happy to take questions.
Yeah, thank you very much, Andrea, for sharing also these exciting new results. Questions? You were first.
Okay. Can you get the inductance information from this experiment, and maybe superfluid density? Inductance
yeah,
information.
I mean, the quantitative, you can forward fit. You can assume a certain change in the optical properties. You can have a model of the device. With enough fudge parameters, yes. In reality, no. You can't really, it's very difficult to back. It's already, okay, the films are thin, so there's no penetration depth problems, but in a wide field measurement, you can convince yourself that you can kind of back out the microscopic parameters. You're talking about the kinetic inductance here, so basically the scattering rate. Basically, the density. Not really. I mean, as I said, you can forward fit, but if you have enough parameters, you can forward fit anything. Yeah.
Thanks for the nice talk. Regarding the efficiency part, when you shifted to this more efficient pumping at 45 MeV, you said that you needed less power, so you illuminate less, and then you have less heating. And I would have expected they have longer metastable lifetimes. Is it something you have seen?
Okay. So the metastable life, with the caveat that we haven't characterized, the experiment is just hard enough that we haven't been able yet to characterize everything. The metastable lifetime seems to, it is long, but it seems to depend a little bit on the phases of the moon, but it doesn't change very much. The point that I would like to make to your question is that we don't think that the relaxation rate is determined by dissipation of heat. Right? Okay. But rather by some rate-limiting timescale. And you have a superheated superconductor, imagine, and now you have a rate-limiting timescale that depends on, you have some rigidity. But I think that the relaxation rate will depend on things like the phase stiffness of this light-induced state or other phenomena that would.
So in a Kramer's picture, is more the curvature of the, of the parabola of your metastable state rather than the height of the barrier and the thermal fluctuation.
What I think is going on, which of course I have no proof for, is that you create this photoinduced coherent state, and the rate-limiting step is the time scale needed to generate vortices in this state. In the same way that, if you take a BEC in the simplest possible, you take a Bose-Einstein condensate and you heat it up promptly above the transition temperature, the rate-limiting relaxation time will be given by the time needed to generate vortices and antivortices. So, and because 2 delta excitations would be far faster than the time scale that we find. Let's say the hypothesis that is informing our experiment is this one. We have no way to prove it. Yeah.
Thanks.
More question? Here's one more.
Excellent work, Andrea, as always. Very fascinating. I want, if you can measure the resistance with the 2-point contact, why not with 4 and settle this once and for all?
So, it's possible that a serious transport person could do this. Generally, the problem is the following. If you have 4 probes, you need to keep the voltage constant at 2 probes, okay? If these pads are capacitively coupled to something and you change the conductivity in time, these guys are going to float like a balloon. So unless you do hard work to keep the capacitance small, to make the capacitance high, it's very difficult to keep voltages constant. I mean, people do this. Serious people do this, but you just can't be. So we haven't figured that out yet. It's just hard enough that we haven't gotten to that point.
Seems like equally hard than this, right?
Maybe. Hard is in the eye of the beholder somehow. I mean, these are hard for us. Anyways, this is where we are. So let's say they're harder than two probes. Okay. Yeah.
One more question, maybe? Yeah, Laura?
I didn't understand. How do you synchronize the 3 pulses in this experiment?
They come from the same laser.
But then, the pump pulse is coming before essentially the other one starts.
Yeah, but you have mirrors.
No, okay, but the point is that how long does it last, the pump pulse?
The pump pulse is short in this specific case.
It's short in time. Okay.
Yeah, it says half a picosecond or something. Okay,
and then the other comes.
But then we rely on the fact that the state is long. I've shown you only one snapshot now. Of course, one would like to. Once we learn how to do this, we'd like to characterize this effect as a function of time. And for example, it's very interesting to see maybe this relaxation time. At some point, this thing is going to become a metal, maybe after only 10 picoseconds, and then the nonlinear current response will go away, right? So it's, of course, a very good experimental question to ask. How long will the nonlinearity last? It's just, again, this is just hard enough that we haven't gotten to it yet. Yeah.
Okay, quick one? Very quick.
I guess just one question. I mean, do you have an estimate of what the HC2 would be, and could you try just doing this in a large field to see if it doesn't happen?
HC1 is very small, and HC2 is a large number here. I forgot what it is. And again, it's just an issue of doing this thing, putting it into a big magnet, delivering the femtosecond pulses to it, having the right windows. I mean, I can't go on, right? Everything can be done. But not simultaneously, not necessarily, yeah. So.
Okay, thank you, Andrea. Thanks a lot. Martin?